Welcome everyone to the New Jersey Institute of Technology's Institute for Data Science seminar series. I'm David Bader, and I'm a distinguished professor at NJIT and also direct the Institute for Data Science. I'm very pleased to introduce our speaker today, George Karniadakis. Professor Karniadakis is from Crete and earned his Ph.D. from MIT in 1987. He was appointed lecturer in the Department of Mechanical Engineering at MIT, and subsequently, he joined the Center for Turbulence Research at Stanford NASA Ames. He joined Princeton University as an assistant professor in the Department of Mechanical and Aerospace Engineering and as associate faculty in the program of Applied and Computational Mathematics. He was a visiting professor at Caltech in 1993 in the Aeronautics Department and joined Brown University as an associate professor of Applied Mathematics in the Center for Fluid Mechanics in 1994. After becoming a full professor in 1996, he continued to be a visiting professor and senior lecturer of ocean mechanical engineering at MIT. And George, congratulations for being a member of the National Academy of Engineering. Today, we're going to hear a talk entitled From Neural PDEs to Neural Operators, Blending Data and Physics for Fast Predictions. George?
Okay, great. Thank you very much, David, for the introduction and the opportunity to talk about neural PDEs and neural operators. This is the area of scientific machine learning, a term that I think I helped coin a few years back, and basically refers to the fact that we could use neural networks to solve PDEs and together with data that may be available. So that's the neural PDE part. And then if I have time, I will also talk about a new type of abstraction at the operator regression level, which is useful for applications like autonomy, discovering black boxes, black box systems, and so on. But I want to start with this unusual movie of a Lstm photography over my coffee cup, espresso. I drink lots of espresso. Of course, this is not a technologically important application, but I was happy to convince this company, this German company, LaVision, to set up an experiment for me where I would have this Lstm photography and different slices so they can reconstruct the thermal gradients. But still, this is very qualitative. I wanted to make a point. I want to make the following point. Can you infer from qualitative visualizations like that, can you infer the full velocity and pressure over my espresso cup in 3D and time? That is something that conventional methods, existing methods, ANSYS, biggest software company in the world, cannot solve. So I wanted to prove a point that using this type of methods, there's a room for it, because you can solve ill-posed problems for which you're missing data, boundary conditions, important information that we comfortably use in applied mathematics and in engineering, although we usually this information is not always available. I'll get back to the coffee example later, but first of all, I want to remind everyone the approximation properties of neural networks, and this goes all the way back to the Saipenko theorem of universal function approximation, or a single neural network, a single layer here. We can write the output y as a linear combination of this construct. This construct is nothing else but a nonlinear basis, if you like. X is the, if sigma was not there, this would be a linear basis, and these are the biases, ax plus b, if you like, and sigma is a nonlinear activation function, could be a hyperbolic tangent, what we use today, or a loose. Now, the theorem says that, of course, if you have a infinite number of neurons, which means degrees of freedom here, you can actually approximate y, a function f, with y, the output of a neural network, with arbitrary accuracy. Okay, so that's known as a universal approximation theory for functions. So it's well known. Later on, I'll tell you something about operators. So this is not unfamiliar to those of us who are working in scientific computing, because we take even a Fourier series can be written like that, some basis times some coefficients, any representation, spectral representations and so on, or finite element representations would look like that, even polynomial approximation functions. So this is not really unfamiliar. Now, when we go to deep neural networks, this viewpoint also is valid. For example, if you take all these hidden layers and stop at the last layer, the last nonlinear layer, and you name this phi1, phi2, phi3, some function basis, then you can write the output as a linear combination of these phis times this these weights from the linear layer. So this is again a linear combination of some basis, but unlike finite elements and spectral methods and so on, this basis is learned by the data directly. So this viewpoint is really the adaptive basis viewpoint is very important for us who are doing scientific computing in order to incorporate this type of expansions, these useful expansions, into a repertoire of methods that we will develop for solving PDEs and making inferences. And here I'm going to talk about the regression, not classification. I believe regression is much more difficult than classification that commercial machine learning is doing. Just as a way of introduction, this is a classroom example of the Range function, what's called the Range phenomenon. This function, if you try to approximate with a Fourier series, you will see this effect right at the endpoints because of the singularity of this function in the complex plane. So Fourier methods, which are the best approximators, cannot approximate this function. So usually what we do is we ask our students to find points, like for example, the Chebyshev nodes, where this function with Chebyshev could be approximated, but they have to be very carefully chosen. Now, instead, what I do here is I use a deep neural network in this, in this movie. You can see that I change the number of neural layers. And if as I increase the number of neural layers, we can nail this function on arbitrary points. Given any arbitrary data on arbitrary points, we can see from this very simple classroom example, we can see the effectiveness of the neural network approximation, especially the expressivity of deep neural networks in approximating any function, including, in fact, discontinuous functions. So there is also theory for that. In terms of those who do finite elements, there is a close connection, and intimate, in fact. If you think of in one dimension, if you think of the ReLU activation function and these hat functions that we use in linear finite elements, you can write these functions in terms of ReLU. So basically, the linear finite element space is nothing else but the subspace of shallow neural network with a ReLU activation function. In fact, these functions could be, as I just told you, obtained adaptively based on the data. So what I want to, the main theme of my talk is today is to not to justify why I do scientific machine learning using these methods. I just told you that, but to actually say why this method is useful for solving real problems, real application problems. And the reason is, academically, what we have been doing for many years is sort of this type of problems where we pretend we know all the equations, especially in applied math, we do that a lot. And then we have some sterilized boundary conditions. We know the boundary conditions, the initial conditions, we know everything, and then we just march forward to solve the problem. However, in most cases, in real applications, we know some of the physics, or we may resolve some of the physics, but we are not able to resolve all the physics, or we may not know all the physics. For example, in reactive transport, you never know non-equilibrium reactions, but you may know the advection and diffusion. So you can write some of these boxes. This is not a black box, a gray box, but then the data will provide the rest of the box. And of course, you can have also black boxes like this. So with the physics-informed neural network, I'll talk about this middle category. And then if I have time, I'll talk also about this operator regression that could discover also black boxes. So what is pins? Pins is a very simple idea that we put on the archive several years ago in 2017 in the context of physics-informed machine learning, which my group pioneered. And now it has become very popular. Thousands of papers have been written about pins. The industry likes it and so on. And the reason they like it is very simple, and I will explain the concept. But industries like Nvidia now, Bosch, and other big companies have incorporated pins into their activities, and they build digital twins of physical systems, financial systems, biological systems, using this simple idea. And here is Jensen Huang in his Supercomputing 19 conference, spending 10 minutes from his keynote to talk about AI for science and physics-informed neural networks. They hire, in fact, one of my postdocs to build this department for them. So what is PINS? PINS is a composite neural network. It's a standard neural network where you have the inputs x1 and x2 in two-dimensional space. Let's say you try to find this vector of two states, u1 and u2. And of course, if you have a lot of data, you look at the mismatch in the least square sense between the data and the predictions of this neural network, and you find all these connections. Sigma is the activation function, which I showed you earlier. So basically finding the weights and the bias, you identify the neural network will give you the two states, U1 and U2. For that, you would need about 10,000 or 100,000 points to have good accuracy. However, in science and engineering, we don't have, in medicine, we don't have 100,000 points. We probably have 10 points or 3 points or 5 points. What we have instead is some conservation laws, for example, conservation of mass, momentum, energy, or some other prior knowledge, in fact. But if we can express this prior knowledge in terms of mathematical operators like differential, like calculus, differential operators, as I show here, then you can express conservation laws and differential equations in terms of these operators. Now, these operators, differential operators, can be constructed using automatic differentiation. In other words, unlike conventional methods where you have to do expansions, here one can differentiate the network itself. So by differentiating the network directly, let's say du1, dx1, and so on, then you really stay within the same parameter space. So if the unknowns, let's say you have a capital theta to represent the bias and the weights of this network, then when we expand to this the physics network, which is on the right, the data network is on the left, this is really an expansion of this network. In fact, every time you take a derivative, it's like you expand by 2, by a factor of 2, the number of deep layers in the standard neural network. Now, having formulated the problem like that, you can then obtain data in a non-supervised way because you have the physics, and this is now minimization of this residual F1 and F2. Think of this as being forces or zero forces in equilibrium. If you try to make that zero, let's say, then you can add the residual for the data and the residual for the physics and form the total loss function. Now, you can also weight this. You can have a Lagrangian multiplier times data plus another Lagrangian multiplier times physics, but you can see that the data and the physics, data versus physics statement is really a seamless blending of one and with the other, because you can transfer using Lagrangian multipliers importance of one term versus the other. So if you get to that point, which is not very hard, as I will show you, then you can use standard optimizers like Adam and LBFGS to obtain the solution as an optimization problem. You don't march forward, you don't discretize in space or time like we usually do in classical methods, in classical scientific computing. So here's an example we give to our students. This is a Burgers equation. It takes about 1 semester to teach our students, graduate students, first year graduate students, how to solve this. This is now done in 10 minutes because with this statement, you define the data neural network in TensorFlow. You can use also PyTorch, or then you can take the physics. You can, as I said, it's the same neural network. So you differentiate using TF gradients in time and space, and then you sum them up to get the residual. You try to minimize the residual. This is this term. Now, visually, what happens is we have the space x, we have the time t. We never discretize. These are continuous variables. And then we have some data. This would be the initial conditions. Could be data at the boundaries. I don't call them boundary conditions because in a classical problem, you cannot have gaps in the boundary like like where I have my cursor. I hope you can see my cursor. There's a gap here. During that time, there's no boundary conditions. So that alone precludes you from solving this problem using any known method. Okay. However, here we have an optimization problem. We have some data, and we have this data, and then I can create data inside the domain by computing from this piece of code and this math formula. I can compute the residuals of this PDE that I have on random points in space-time. Doing that, 10 minutes later, you get good-looking solutions like this, which avoid overshoots, avoid Gibbs phenomenon, which you would have with standard methods, because, as I said here, we have an adaptive basis from the adaptive basis viewpoint that I explained earlier. So that's the idea. You blend data and any data, this could be boundary data or inside the domain data, with physics. You compute physics at all random points. This is now an extension of this idea. This is called XPin or extended pin, because it uses two subdomains. One for the same exactly problem, but here we have one domain where the certain physics is happening. Let's say this very steep gradients where the dolphin is, and then outside the blue part is the blue sea, I call it. It's the other network. So I assign one network to the dolphin, and I assign another network to the blue sea. And the reason I do that is because I want to train smaller pins faster and in parallel. So independently and only using point-to-point communications, I can bring, because I need to stitch the domains together through this red line. And how do I do that? By penalizing the residuals to be 0 at those points, because we need to satisfy the physics. So I have a nice parallel scheme with domain decomposition in space-time. There are not many methods that can do parallelism in time, as you know, but this is an arbitrary decomposition, and that's why the shape is here as non-convex, to show that you can get the same thing as before. And I have a picture here to show the seamless stitching of the two domains together. We also have theory that will tell you a priori how do you go about decomposing like that using this method, the domain decomposition method. As I said earlier, there are many people who have picked this up, and they have produced better results than the original results. For example, one of the questions for multi-rate problems was, how do you actually weigh the various terms in the loss function? You have boundary terms, you have initial conditions, you have the equation, you have data. So this paper here by, I call him Clever Ulysses, because he solved a problem I couldn't solve. So Clever Ulysses introduces lambdas, these Lagrangian multipliers, which are actually functions, not constants. Now, how do you know that? How can you find them? It turns out that you can reformulate the problem in terms of a steepest ascent, so you can find the best weights that will give you the fastest training of this pin. And here's an illustration for this, what is called the Bad Boostiness Equation, because it produces waves which travel in different directions, as you can see here. This is a solution of this equation, and the corresponding weights are now fields. Lambda will depend on x, y, and t and time. But let's say at one instance, what you see here is these weights follow the solution, as you can see. So this solves this problem of data balancing. There are other advances that, for example, my group also came up with this idea of adaptive activation function. This is good not just for pins, but for any neural network. As you know, artificial neural networks are really not very smart. They're not human-like neural networks. Human neurons, every neuron will fire at different rates depending on the task at hand, and also depending on its position in the neocortex. So what we did is to introduce adaptive activation functions, so that not every neuron will fire at the same rate. So you can see here now every neuron has its own activation function, or you can have sort of a classes of for different layers. You can have a whole vector of activation functions like that. Now, how do we make them adaptive? Well, at the simplest form, for example, in hyperbolic tangent, you can have a parameter that adapts the slope of this, how steep it is. So every depending on the data, every neuron will fire differently. And that works pretty well, but in this Kronecker, we generalize this to this type of composition, as I show you here, where we introduce this what we call Rowdy activation functions. Instead of just having the slope of this hyperbolic tangent, which is the activation function, to be varying according to the data, we also superimpose these perturbations, because early work on machine learning neural networks found that if you have stochastic perturbations, then you actually never get into a plateau where you're trapped, and then the training doesn't happen. So in fact, we have theory now that we show that in this Kronecker neural network and this adaptive activation function, the loss function is always smaller than a standard feed-forward neural network. So this is solid theory by analyzing a two-layer neural network. We also show that the initial decaying of this function is exponential, with just having some mild assumptions for the theorem. So we guarantee, in fact, that this is the fastest training. And we know it works really well for pins, but here I want to show you that for standard computer science benchmarks, like the CIFAR 10, CIFAR 100, MNIST, and so on. Let me concentrate on CIFAR 100, which is perhaps more difficult than the other ones. You can see here the Rowdy activation functions converge the fastest, both in training, this is the green line, and testing. And this is better than any of the state-of-the-art using any other method. The method is very simple. So high school students, like this one here, is Jeremy Yu. He's a high school student, 17 years old, who did a summer internship at MIT last year. So he was able to introduce some innovation. For example, he introduced this term to the loss function, which instead of just the residuals, we can also take the gradients of the residuals. And by doing that, it turns out that you can enhance the accuracy. And here's an example of that. Let's say you're trying to solve an equation like that, a diffusion reaction system, for example. And when you penalize, a standard pin would look like this, the error versus the number of training points. However, the gradient, if you take the gradient of the residual, the convergence is much faster. Eventually, of course, if you have lots of points, the errors are the same, but of course, this pays off if you have a few training points. Of course, you have to take higher derivatives, and that's expensive with automatic differentiation, but current research and JAX and other languages provide better ways of doing automatic differentiation, so that will also be something positive in the near future. Okay, let me go back to the coffee example. And this is something we published in Science 3 years ago, and we call it the hidden fluid mechanics. So it basically makes this point that how can I take a visualization, something qualitative, and turn into quantitative? How can I look at let's say satellite images of the ocean, of the surface, of the sea surface, and extract currents, if you like, ocean currents? So here's as an example, what we had is, let's say you see this video of where the dye flows. Can you extract the velocity and the pressure without any knowledge, no boundary conditions, no Reynolds numbers, nothing? So then you postulate some equations like associated with the dye is a passive advection diffusion equation. Then you add to this what you believe is a parameterized Navier-Stokes equation. And then you have data from the dye, and then you transfer within the same network, same parameter space. You can transfer, if you learn these parameters, then you can basically know also U and U velocity, V velocity, and the pressure. And this shows some of the results that indeed you can go from secondary auxiliary data to the real data. I will demonstrate this for a real problem. This is intracranial aneurysms, brain aneurysm. This is a brain artery which is dilated. And this is some contrasting agent that a neurosurgeon would inject into the patient. So we'll see if there is what is going on with the aneurysm and when the neurosurgeon will have to operate. That's totally qualitative. They just use the naked eye norm to do that. And we want to basically say, can we make this rigorous, and can we provide the clinicians with knowledge to know exactly when to operate? And so the only information you have is this flow of this black and white dye. And again, using this imaging, we can model that as an advection or advection diffusion of this dye, and then we couple it to some parameterized model for the flow motion, and then we can actually, using just the dye as a data, we can obtain all the information we need, especially all the detailed information inside this aneurysmal sac. If you have this information, you can compute the forces at the aneurysmal wall, and therefore you can decide when this will rupture or not. Going back to my coffee example, what we have is really this data from LaVision. This is the data on the left. The neural network will match it. This is the output of a neural network, which you can see in one plane. It's 3D, but here I just show planar slices. We match it, and then in the process, we also discover the pressure field and the velocity field over the cup. So there goes my 30-year quest for answering my question. Every time I drink coffee, LaVision solved it for me. The reason LaVision decided to do that is because early in the pandemic, March 2019, we found this video. This is now my collaborator, Thomas Berg from Göttingen, who was puffing with and without the mask. And I asked my postdoc if he could possibly take the video from YouTube and try to assign some quantitative information to it. And indeed, using with the method that I just told you, we could quantify the velocity and the pressure field. What you see here on the left is the pressure, here's the velocity. So you can see the individual vectors that we quantify out of nothing. We didn't know the guy now we are friends and collaborators. But the point is, we found that wearing a mask can reduce, for example, the initial flow of droplets by up to 10 times. So that was something that you started with something from YouTube, and finally you can find something useful on YouTube and turn it into something useful anyway. There are other applications of non-destructive evaluation of materials. For example, this group from the Air Force, and also in Europe, they have these little robots go around and look at specimens and take imaging and so on. I want to show you how we can characterize, and this is work that was done the Air Force, right? Patterson. These are alloys for aluminum alloys are used in gas turbine blades or other materials that are used for planes that we're flying. And sometimes they have these surface cracks, and that could be scary. So, but they're tiny, so you cannot identify it. So that you have this ultrasound, for example, that you strike ultrasound, and from the reflection, you try to identify where's the crack and can you fix it. So this is real data. This was actually a hackathon that we have for DARPA for one of our projects. And there were 12 teams, and they gave us ultrasound data. Ultrasound data, every team complained that they didn't have enough data. We only used 10% of the data. And we use 10% of the data because we use the physics. So you see, here's a pin that I have, which will solve some equations, the wave propagation. But I make that the speed of the sound to be a function, xy, a known function, because I know it is now a heterogeneous material. If it's a homogeneous material, this will be a constant, and you look it up in the textbook. But if it's heterogeneous, you don't know that. If you know that, the zero contour is where the crack is. So we assign, together with a pin, we couple this to another neural network, which will represent this variable speed. Then we minimize this, just a standard loss function, and we solve simultaneously both for the pin, which will give us this psi, from which we can get all the information we want, the acoustic wave, plus this velocity. And I don't know if you can see here, but this is a setup. And this is on the left, we have the real data, 10% of the data only. On the right, we have the pin that reproduces data. And in the process, it can find the zero contour, and therefore it can find the crack. It's like looking for a needle in a haystack, but can do it very, very accurately. So this is just an example of, just another teaser here for those of you who are interested in drones. We flew 256 drones at the same time. And what you're looking at is drones are trying to avoid collision while they're trying to go from one wall to the wall across. Let me wait until this plays back again. So we start from let's say from each wall, there's a layers of total 256. All this here now, the drones are leaving their origin and trying to go across. It's hard to follow so many drones. They try to go across to the other side without hitting anybody and going there as the fastest possible time. So these are 256 drones in 2 dimensions. That's 512 dimensions. So to solve this problem is impossible. We solve this problem on a GPU in less than 1 hour by applied math student. So that's kind of combining pins and what's called symplectic integrators, and also these Hamilton-Jacobi equations for preserving the structure of the that you need for long-time integration. There's lots of pins. I don't have time to talk about this. I know you're not an applied math department. You are a data science department, but as I said, data and PDEs help each other here in this example. We wrote a SIME review paper that explains this, and there's a library DeepXD that has been downloaded 300,000 times from GitHub. X here means any differential equation. XD means any. You can solve this. You just dial in the equation. All the infrastructure is there, both in PyTorch and TensorFlow. The industry is many companies, Nvidia and Ansys and Cummings and so on, are interested in this stuff. Okay, so that's the first part of my talk. I want to show you this autonomous naval destroyer that is trying to go through the Atlantic Ocean at waves of 20 meters, sea state 8 for those of you who are sailors. Don't go out in the sea when the waves are so high. But the idea is, of course, can you do autonomy and can you use neural networks to do real-time predictions? And the answer is no. Here, for example, this is a simulation done by MIT students who are very patient students. And it takes them about 1 week to use a computer code called OpenFOAM to do one realization of it. Okay, so I was interested to see if we can leverage all these runs and all this hard work of the students, put them in a neural network and predict the motion of the vessel, because that's what you need in real time. In other words, can I approximate, the abstraction of that is, can I approximate functionals using neural networks? And if you, back when I started working on this, on functional approximation, there was not much. There are blogs here and there in the modern fashion of science. Everybody has an opinion, but no theorems. So I was looking for a theory, and I found a very nice theorem that says, yes, indeed, neural networks can approximate, functionals. In fact, this theorem was developed at the same time as the Saipengo theorem. And that theorem says that a standard single layer neural network can approximate a functional f of u. U is a function, so it's a function of a function. And if you sample this function from a continuous, function is continuous, from a compact space, you can sample it with m sensors. Then you can see here you have a sigma is an activation function. So again, with arbitrary accuracy in one dimension or multi-dimensions, you can have good approximation, universal approximation theorem for functionals, not functions. Okay, so if you know that now, today we can solve this very quickly because since you know that can be approximated, you can find now, can I have off the shelf, like for example, can I use an Lstm or other network? So indeed, it turns out that you can train a neural network. It takes offline about a month or more to train this because of the expensive simulations. But after you do that, and you can also blend with experimental data, you can do predictions of the sea state, the motion, heaving and pitching and so on in 0.01 seconds. So in real time, really, you can, so you can help this, the autonomy as well. Now, that got me thinking, if we can approximate functionals, can we also approximate arbitrary nonlinear operators? And by operators here, I mean any operators. For example, it could be mathematical operators. It could be stochastic operators, could be anything that you cannot express mathematically. It could be something that maps a nonlinear map from one infinite dimensional space to another. So to that, we went to human neurons, as I describe it here on the right. We have dendrites, we have these branches, which take different inputs. And then we have the soma, or the trunk. And then we have the axon, and then we have the where the output is. So we designed something like that. We have here, this is one branch, one dendrite, that's the input. And so let's say for math, if we want to train this operator to solve PDEs for us, we will have as an input many functions, many different functions. Then we have a output space, continuous output space X. Then we cross them like that, get the output just like in a human neuron. So we published this paper. We actually first came up with this idea in 2019. And again, I was looking for theory. And as I see you, I'll tell you, there is theory regarding this. But I just want to make this contrast, right? What we're doing so far, let's say in image classification, the input is data and then the output is data. So we map a finite dimensional space to another finite dimensional space. What I'm talking about here for operator regression is we have a Banach space, an infinite dimensional space, to another infinite dimensional space. And that covers every category that you can think of, also systems, social systems for which you don't have the mathematical equations to govern them. Okay, so there's a theory, and in fact, the theory comes from the same Chen and Chen pair from Fudan University, who about the same time as everyone else was doing theory in the early 90s, they said, indeed, even a nonlinear continuous operator could be approximated, G of U of Y, could be approximated now by two pairs of networks, just like I show you, in fact. One would be the trunk, which is associated with the output, and one was the input. And you can have multiple inputs, but here, let's say one input. So notice that I have two sigmas for a single layer. That means, because they were talking about single layer in the 90s, that means I have two different neural networks like I show you. So in fact, if we look at the mathematical equation here, and now you can realize this as a hardware, let's say, or a construction, you can see this one here is the trunk, and then this part here is the branch. And you can think of this as a number, bk, which I have here, b1 to bp. So I have a sum of bk's times a basis, like I was telling you earlier about the adaptive basis, but now at the operator level. So basically, this is an expansion of an operator in terms of some adaptive basis, which the trunk gives you. And then by crossing the branch and the trunk, you can get the output. Now, it turns out that this is not enough because single layer neural networks are not expressive. They suffer from the curse of dimensionality, in fact, for operators. So what we did is we replaced the single layers with the deep neural networks, and we prove in our paper in Nature Machine Intelligence, we prove that you can have also a universal approximation theorem for deep neural networks. And by doing that, in fact, you tackle the curse of dimensionality. So you can learn parametric PDEs, you can learn high dimensional operators, which without breaking the bank, without the explosive cost of the curse of dimensionality. So what I'm talking about here is the following. Let's say you're mapping a function u to g of u, right? So you sample u, okay, you characterize u somehow, and then the output, you know g of u. You don't know the g of u everywhere. In fact, if you look at panel B, I sample my input at some points, let's say 100 points, but I sample my output only on 1 or 2 points. And this is important. We found that empirically because the output is where you pay money. The output is where you have to do experiments or very expensive simulations. So, but we don't need the output to be evaluated at a few points. So after you do that, let's say 10,000 times, you learn the operator G. Now, you don't need to do any further training because G can solve equations for you. G can do Laplace transforms for you. G can do integration for you. G can do classification for you, whatever. Okay, so let's do integration, this pedagogical example. Let's say I'm trying to take the integral from 0 to x of this function, and I want x to be from 0 to 1 or 0 to infinity to make this a Laplace transform. So after I train this network to do integration, you give me, here's 1D, could be in 5D. Then you give me any function, so I should be able to integrate it in 0 time because I'm not doing training anymore. I'm just doing inference. So indeed here, I take 10,000 functions, I evaluate S only at one point for each function, not at lots of points. And then it turns out that we can learn very quickly, this is error versus number of iterations, down 10 to the minus 5 accuracy. So it generalizes well for different unseen data, unseen functions. This can be done for arbitrary operators. I don't know if you know about fractional operators, for example, used in finance and other Levy everywhere you have non-normal statistics. Fractional calculus is important if you don't know it. But anyway, one of the derivatives called the Caputo derivative, which, as you can see, is a sort of a convolution of this singular kernel with a derivative. So it accounts for memory effects and so on. So it's an expensive operator. So I wanted to learn this Caputo. I wanted to train a neural network to make the point that DeepONet can learn any type of calculus, including fractional calculus, stochastic calculus, and so on. So basically, you take lots of functions for which you know the fractional derivative, and after a while, you train it. But the point I wanted to make is, so far, my input space where I draw functions was this Gauss random field. Instead, here, I chose to also represent my input space V with spectral polynomials, which are more expressive, and I was able to reduce the error by a factor of 10. So the input space V is really important in this type of. I have another case where I show how this DeepONet can actually learn these differential equations, which describe bubbles, the growth of bubbles. Now, I'm not going to bother you too much, but basically, it's a nonlinear equation. The solutions for given pressure. So the input will be something like that, arbitrary distribution. The output is a multi-rate distribution, as you can see, very fast oscillations, then a decaying part. And these are 3 different excitations for unseen data. So it generalizes well. Now, I have a comparison with Lstm, because Lstm, which I used earlier for the autonomous vessel, it can be useful. But it turns out Lstm and DeepONet give you the same answer if you have lots of points per trajectory of the bubble that is growing. However, if you have only 20 points per trajectory, Lstm totally misses the multi-rate component, the high frequency component, where DeepONet works very well. So DeepONet actually can totally replace RNN and be used very effectively, because it's not as expensive as Lstm, and also it uses only 10 times less data than Lstm. So I will skip that. I just show you that it can learn also from other noisy data. But DeepONet is really something closer to biologically plausible human neurons. For example, and here is I color code everything, so you can see these are the branches, and the branch could be an RNN, could be a CNN if you have imaging data from multimodal input. It can be a feed-forward neural network, and then the trunk itself could be PCA modes. It could be, if you want to bias it, if you want to look at multi-scale problem, it could be Koopman modes and so on. So the combination and the synchronizing and having those 2 networks working synergistically is like having this human neuron processing the data and communicating this information downstream, as I show here. So it is really a plurality of operators, not just one operator, if you like. I will skip this. There's theoretical work associated with that. This is 120 pages of mathematical proofs. That, for example, one main proof was that DeepONets can break the curse of dimensionality. Others is that it doesn't have to be a continuous operator. In fact, it could be a discontinuous operator, which is important. How do you sample this vast input space? It turns out that surprising result was random choice of sensor points for the input was enough to provide an almost optimal encoding error with very high probability. So this, so there are technical issues that I don't want to talk about here. But when we wrote our paper for DeepONet, Irina Higgins from DeepMind wrote a 2-page cover article in the same issue of Nature to praise. And as you know, DeepMind don't praise others because they're sort of self-admired for all the great things they do. But they actually told us things that we wouldn't know. So they suggested that we could use this for complex systems like learning social dynamics, and that you can learn all spatiotemporal scales. I think we knew about that. We didn't know that they can even use this for social dynamics. And in fact, some teams around the world are actually working on that right now. DeepONet, because it doesn't need any training, it's very fast, 1,000, 100,000 times faster than any existing solvers. So Quantum Magazine had a special article on it last year about these results. Now, I want to finish with this kind of pessimistic note. There's a lot of hype in the last, let's say, 10, 15 years about neural networks, and I think justifiably so. There are lots of successes. And the question is, where did that all success come from? Of course, people like Hinton were instrumental in tell us what to use, what methods, and then people will improve by 0.1%, 1%, and so on. But this recent study by Neil Thompson from CSAIL from MIT showed that a lot of this success came from the hardware. If you go back to 1993, for example, here, this is where Nvidia started, you can see that that hardware performance was really right here. Now, deep learning at this point needs much more computer time that is available. This is the computer time that's available, and then deep learning is this red curve. So obviously, this is not sustainable. In fact, as you know, some of these GPT-3 transformers, Elon Musk and so on, they pay millions of dollars for one training. There was some mistake on GPT-3, and they asked Elon Musk to retrain it, and they said, look, it costs $5 million every time I train it. So you see that these are very, very expensive. Nobody talks about how expensive are actually these, and they're not sustainable. This is not sustainable. This cannot be used for edge computing, for example. A robot cannot go around with 100 or 1,000 GPU nodes on its head. It will not work that way. And using the cloud doesn't work because there's delay, there's all sorts of issues and so on. So there is some at least some people who are serious about it. They're thinking on what do we need to do. Some people say symbolic computing. Some people, of course, talk about neuromorphic computing. For example, the new Intel Aloihi 2 processor by Intel consumes 50 milliwatts, not 50 watts that an Intel or 100 watts an Intel processor would consume, only 50 milliwatts. That's like 1,000 to 2,000 times less power. So that's very important because if we keep improving, the same article makes the point that if you want to improve ImageNet down to 1% error, you have to spend so much electricity that will be equivalent to New York City 1 month of electricity bills, leaving the same footprint of carbon, and therefore this is not very friendly and nice to the environment, never mind the cost, which is tremendous, especially these days. So this is not a sustainable picture. So it seems that there is some skepticism and reason to rethink on how we can, in my case, I go to sort of more biologically plausible neural networks like spiking neural networks. So my group is working on that. There has already been some work on spiking neural networks for classification, but of course, as I said, we are interested in regression. Can we infer things governed by conservation laws and so on? So I don't have time to talk about all the math that goes behind this, unlike standard numerical methods where the approximation error dominates. Here is really the generalization error and the optimization error, which dominate not only for pins, but of course for any neural network. And this is the holy grail, is really the optimization error. How can we bring our errors down to smaller levels? For some classification systems, of course, recommendation systems like you recommend shoes and so on doesn't matter too much. But for scientific problems, this matters a lot. And with that, I would like to also make an advertisement for a course that we have developed for Nvidia, which will be free on the web for those of you who are interested in deep learning for scientists and engineers. It will have these modules. Module 1 is all about basics of neural networks. We will teach Python and also PyTorch and TensorFlow. We teach all the basics and the math behind it. Then module 2 would teach things on neural PDEs and neural operators like I discussed here. And then module 3 is more computational oriented. DeepXD is our library. Modulus is a library by Nvidia. And then we'll also talk about multi-GPU and scalable scientific machine learning. There are also 20 projects from biomedicine to dynamics of climates and other applications that people can select from. And this is all will be free to download from the Nvidia website. My sponsors are the Department of Energy. I'm directing this. I think it was the first big center on physics-informed learning machines. We are in the process of renewing it with emphasis on spiking neural networks. And also we have as MURI from the Air Force on learning and meta-learning. I didn't talk about meta-learning here, how you actually do neural architecture search for this type of physics-oriented problems, but that's one of the problems. And this is my last slide. I would be happy to take also questions. Thank you very much for your attention.
Thank you, George. Fantastic lecture. Let me ask the audience if there are questions, and you can either use the chat or if you want to unmute yourselves and talk, that would be great as well. I do see that there is one question in the chat from Denzel Serrano that asks, are all the works mentioned here that use pins supervised methods? Are there any existing literature that solves PDEs with just initial parameters and physics laws?
Yeah, sure. Without data, you mean? Yes, of course. I wouldn't say that pins are the best method for solving just standard sterilized problems. I would think like spectral methods or this type of methods would be more accurate, more appropriate. Pins were developed to solve kind of hybrid problems where you have a little bit of data, sort of data simulation, a little data and little physics. But certainly they can solve problems forward. So there's a literature on that. Usually we do some of this just to show that as a sanity check. But it's as I said at the end, it's very expensive to do these solvers compared to mature, accurate spectral type solvers or finite element solvers for the forward problem. Inverse problem is different. Inverse problems, pins outperform any method by factor of 100,000, a million, and so on, because the forward problem, the inverse problem for pins is exactly the same. But as you know, for other methods, you have to write different codes, adjoint, and so on, and that's the difference. So the strength of pins would be the inverse problem, not the forward problems. Yeah.
Thank you. There's a question from Frank Giraldo.
Yes, thank you, George. Excellent talk. I really enjoyed it. Very impressive results. One of the questions I had was, so it was good to see that there is a lot of mathematical rigor behind what we can do with these neural networks. So that Chen and Chen theorem that I actually became aware of from one of your papers that mentioned that. So it states that the neural network can approximate continuous functionals, but you said later that we can also extend it to nonlinear functionals, right? And then the other thing I was going to say is
discontinuous, extended to discontinuous, yeah. Nonlinear, it's all nonlinear, yeah. It's all non, yeah.
But then if I look at that paper, I haven't read it in detail, but it seems to me that they rely on these sigmoid functions, does it matter whether we use, like, say, ReLU or any other kind of activation function?
No, as long as it's not, I mean, this is also true for neural network standard functional approximation. As long as you use non-polynomial activation functions, it's fine. Sigmoid is one type, but of course hyperbolic tangent is the same thing. ReLU is the same. ReLU is not appropriate for pins because you have to take derivatives and it's not differentiable, right, before the first derivative. So I wouldn't use ReLU for that. But for the DeepONet, where if I don't use the equation for DeepONet, you can use ReLU, no problem. Right?
Great, thank you.
But the extension by Sid Mishra, myself, and his student is actually for Borel measures. So you can do discontinuous operators. I didn't show the bubbles, but I was putting together molecular dynamics data with continued data to construct a multiscale operator. DeepONet doesn't care, and actually that's a discontinuous, right? Because operator from continuum regime to molecular regime. So we didn't have the proof at the time, but actually now we have a proof that that the Chen and Chen theorem. If you want to read the proof, actually we have a much simpler proof in our paper, a constructive proof for deep neural networks, which will make more sense because we follow like a Fourier method type and constructed. Yeah.
Thank you, George.
So I have a question about the architectural requirements. You had mentioned that hardware has really been the enabler to allow these large neural networks to be trained and operate. And we see different architectures emerging for training large architectures versus those that are used in computational physics. Do you have any thoughts on what is the right architecture that's needed for pins? Is it going to look like what we have now with GPU accelerated commodity processors, or will it look more specialized?
Yeah.
For instance, the training architectures that we see.
Yeah, at this point, the A100 Ampere A100s of Nvidia are really the best hardware for pins. But as I said, this is high performance hardware, right? You're not going to have that for edge computing. You're not going to have it for mobile platforms. So there is a trend. There is interest also from DoD to go to adaptive arithmetic with TPUs. Some of it could be, this question, David, it goes back to 30 years where we're trying to find which low arithmetic operations are useful, right, in scientific computing. But it's actually very important now because we want. So my group is trying to sort of go to the next generation of pins. We call them cheap pins that would really require very little energy. An effort to go to spiking neural networks is that, and neuromorphic computing, but really reducing the operation cost, accelerating the big bottleneck, not just for pins but for neural networks, is really optimization. And just like in numerical analysis, scientific computing, before multi-grid, I don't know if you were working at that time with methods like Gauss-Seidel. We could solve the problem, but it was so expensive. And then the big algorithmic jump was when Ike Brand came and said, okay, here is the multi-grid, and we got a boost of a factor of 1,000, right? In some problems or more. So that's what we are waiting. We're waiting for this big algorithmic boost. That's why I show at the end the steady rise of Nvidia and so on that got us here. But we really don't have a huge boost yet. We don't have that boost, and of course it's not an easy problem. Is a non-convex optimization of a non-convex high-dimensional function.
Uh-huh.
So, but anything to accelerate the optimization part will be a huge breakthrough for all aspects, all facets of neural networks, including, of course, scientific machine learning. Yes, but I don't know to answer your question. We kind of do like MPI plus X. X could be a mix of CPU, GPU right now. That's how we scale up systems. Yeah.
Thank you. There's a question in the chat from Yufeng Liu, who asks, could PIN perform forward time evolution? If we train the network on time interval A to B, could we apply the trained network for a different time interval? Will neural operators be able to do that?
Good question. Pins, of course, can do that because they have the equation, so we train them every time, just like every solver can do that. DeepONet could do it so well because we train it within a certain interval. It can approximate outside the distribution, we say, probably with an error of 20%. But so it can be used as a transfer learning method. Because we don't train it at all, so don't expect it to extrapolate. Certainly, it extrapolates. The richer, the more exhaustive the search of the input space is in the offline, the better it generalizes outside the distribution. But of course, it cannot do that. So I was solving for the DARPA problem. I was doing a hypersonics problem for which we demonstrate the 100,000 speed up for Mach number 8 to 10. Where we train the network. And then my program manager said, yes, but the Russians are chasing us and we have to go at Mach number 13. How do you do that? I said, well, I cannot do that. You need to give me new data. So he said, okay, but I only have 3 temperatures and 2 velocities because it's hypersonics, right? And so then you have to assimilate. So we use DeepONet, the train, as a transfer learning method. Initial guess, and then we assimilate it with another supervising neural network, the new data we assimilate, and then we train them very quickly also, not real time, but almost real time this. So you cannot extrapolate, you can extrapolate, but you'll get an error with just a few data, you're almost there, you can get good answers. Pins can extrapolate, DeepONet can extrapolate a little bit.
Thank you. Are there any other questions from the attendees?
Can I ask another question?
Sure.
Yeah, thank you, Professor Karniadakis, for the answer. So how about for a chaotic equation? For example, if our equations actually have a chaotic actual pen or neural network or the operator to really quantify this chaotic, or can we actually capture that?
Yeah, very, very good question. Very good question. That's a sort of an open issue. So in one of our papers called NSFNet, Navier-Stokes flow nets, we try to address that for turbulence, but we actually had boundary conditions were given, the data were given by DNS, so it was like observers, right? So if you do the Lorentz system, you can do with pins, you can do it if you do it very, very accurately, but with DeepONet, you will lose accuracy at some point, of course, as you extrapolate. If you have a strong positive Lyapunov exponent, that will be difficult. However, if you have observers, if you have some observers, some sensors that will give you some data, then you can do very long extrapolation using either pins or DeepONet. But it goes back to the accuracy, to the lack of really, really high accuracy that you have. We don't have the accuracy that spectral methods have. So if your Lyapunov exponent is such that the initial conditions, you change them by 10 to the minus 14 and the trajectory change, pins will give you the wrong answer. But if you have one observer, just like a Kalman filter, if you have one observer basically to correct the trajectory, you can get it very accurately also. So that's the difference between spectral methods. Because of the high accuracy, you can track well into the chaotic regime for some time, but not with pins, not just with pins and no data.
There's one final question in the chat asking about the link to the Nvidia course. I know many of us will want to see that and watch that course. Do you have any pointers to it yet?
Not yet. Nvidia will make an announcement. So I don't really have that information, but we have finished. There's like 15 lectures with videos and Jupyter notebooks. As I said, everything will be available, and Nvidia will make the announcement. It will be free for everybody to download, as I said. They have this already. If you go to their teaching institute, they have some, I think LeCun has a free lecture also there for them, for CNNs and so on. So that's what they try to do.
Well, again, George, thank you very much for giving this lecture. I learned a lot, and I'm looking forward to the Nvidia course. I know I'm going to learn even more from that. And thank you for everyone who's attended it as well.
Thanks, David. Good to see you.
You too. Take care.
Yeah. Bye.
Take care, George.